you to the lecture for section 13.1, and this is MGF 1106, Liberal Arts Math, and my name is Jorge. So this is the lecture for 13.1, and in chapter 13, what we're going to talk about is probability. So in 13.1, we have four objectives. And the first one is we're going to calculate probabilities by counting outcomes in a sample space. We're going to use counting formulas to compute probabilities. Then we'll understand how probability theory is used in genetics and also understand the relationship between probability and odds. So the first thing is, let's talk about sample spaces and events, and then also what's probability. Now, random phenomena are occurrences that vary from day to day and case to case. So although we may never know exactly how a random phenomenon will turn out, we can calculate a number called a probability. So here's a definition. An experiment is an observation of random phenomenon. The different possible results of this experiment are called outcomes. Now, the set of all possible outcomes for an experiment is called the sample space. So here's the first example, right? Determine a sample space for the experiment of selecting an iPhone from a production line and determining whether it is defective or not. So the sample space then would be either defective or it's non-defective. So here's the next example. Determine a sample space for this experiment. So 3 children are born to a family, and we note the birth order with respect to gender. So when we do that, we'll end up with boy, 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 girl, all the way down to girl, girl, girl. And all of the different possibilities are what we call the sample space. Now we can also use a tree diagram to do that, and here it is. So the first birth, boy, girl, the second birth is determined after the first birth already has occurred, and in the third birth, of course, after the second and the first. So that's why we can have boy, boy, boy at the top, or girl, girl, girl at the bottom. So here's another example. We roll 2 dice and observe the pair of numbers showing on the top faces. So the solution would be a sample space consisting of 36 listed pairs. And here are the 36 listed pairs. Now this is very similar to one of the questions on the test that we just had. So we roll the first die, we get a 1. We roll the second die, we get a 1. That'll be a 1, 1. And that all the way down to getting a 6 and then a 6. So here's another definition. In probability theory, an event is a subset of a sample space. Now, although we describe events verbally, you have to remember that an event is always a subset of the sample space. So if it's not a subset, then it cannot occur if we're just talking about that particular sample space. So here are several examples, right? So each one of these is a subset of a sample space. The first one, a head occurs when we flip a single coin. 2 girls and 1 boy are born to a family, and the sum of 5 occurs on a pair of dice. So the solution for the first one is that the set head is the event, because we're only going to flip a single coin. Now, the next one is the event is boy, girl, 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 boy, girl, or girl, girl, boy. And then the last one is the event is 1, 4, 2, 3, 3, 2, and 4, 1. And actually, for the first one, if I flip a single coin, since you would think that it would have to be heads, tails, but we're looking for a specific event, a specific outcome, and that's why it's just head. So here we have some more definitions. So the probability of an outcome is a sample space, is a number between 0 and 1 inclusive. Now the sum of the probabilities of all the outcomes in the sample space are always equal to 1. Now the probability of an event E, written P of E, is defined as the sum of the probability of the outcomes that make up E. So here's the empirical assignment of probability. So if E is an event and we perform an experiment several times, then we can estimate the probability of E as follows. So P of E is equal to the number of times that E occurs divided by the number of times the experiment is performed. So this ratio is sometimes referred as called the relative frequency of E. So here's an example. A company is testing a new drug. The company injects 100 patients and obtains the following information. Now, based on the table, if a person is injected with this drug, what is the probability that the patient will develop severe side effects? So here in the table, we have side effects. We have none, mild, or severe. We have 72 for none, 25 for mild, and 3 for severe. That's a total of 100. So now we obtained the following probability based on the previous observation. So the probability of severe side effects is the number of severe side effects that occur, number of times that occur, which is 3, divided by the number of times the experiment, which is 100. 3 divided by 100 is 0.03. Here's an example. table summarizes the marital status of men and women in thousands in the United States in 2006. So if we randomly pick a male, what is the probability that he is divorced? Now, we have to be careful here because here we're saying if we pick a male. So now we're just looking at the row that has males. So what's the probability that he's divorced? So then we look at the cell that has the divorce and we have 10,818. Now total males in this one is 116,326. So now we can find the probability that if we randomly choose a male that he's divorced. So again, the total males 116,326, and then the total of the event D, which is divorce, is 10,818. So we divide those two, and that's approximately 0.093. It's about 9.3%. Now, counting and probability. Now, probabilities, there are two types. There's empirical probability or empirical information, so we base it on something, on a trial, if you will. And the other one is theoretical, and essentially we can get this off of formulas. So now, if we flip three fair coins, what is the probability of each outcome in this sample space? So now each one is equally likely. So each has a probability of 1/8. And here are the all of the 8 possibilities. Now we draw a 5-card hand randomly from a standard 52-card deck. What is the probability that we draw one particular hand? So here we found that there's a combination of 52 objects chosen 5 at a time. Is 2,598,960 different ways to choose 5 cards from a deck of 52. Now each hand has the same chance of being drawn, so the probability of any particular hand then, it's 1 divided by 2,598,960. Now, calculating probabilities when outcomes are equally likely. If E is an event in the sample space S with all equally likely outcomes, then the probability of E is given by the formula of P of E is equal to the number of E divided by the number of in the sample space, or the outcomes in the sample space. Now, if the outcomes in the sample space are not equally likely, then we cannot use this formula. In that case, we can use P of E, and then we must add the probabilities of all in the individual outcomes in E to get that. Now remember, like I said before, if I add the probability of all of the outcomes within a sample space, I should get to 1. So here's some basic properties. Assume that S is a sample space for some experiment and E is an event in S. So the first one is that the probability of any event is between 0 and 1. It could be 0 or it can be 1 or in between. The other thing is that the probability of the empty set is 0, and then the probability of all of the events, or the sample space, is 1. So what's the probability of 1? That means that it's going to happen. What's the probability of 0? That means that it's pretty much impossible. So what is the probability in a family of 3 children that 2 of the children are girls? So now, we saw earlier that there are 8 outcomes in the sample space, and we denote the event that 2 of the children are girls by the set G equals, and here you can see the 3 possibilities that when you have 3 girls, if you have 3 children. So now, we know that we had 8 possible, the sample space is 8 possible outcomes, so 3 divided by 8 will give us the probability that a family with 3 children will have 2 girls. Now, what is the probability that a total of 4 shows when we roll 2 fair dice? So again, sample space with 36 different events or outcomes, and then we're going to go ahead and represent this by F, the rolling of 4 by capital F. So then there are 3 possibilities. So it's 1, 3, 2, 2, or 3, 1. So then we know that we had 36 in the sample space, so 3 divided by 36 is 1 over 12. So the probability of rolling a 4 is 1 out of 12. Now, if we draw a 5-card hand from a standard 52 card deck, what is the probability that all 5 cards are hearts? So this one's a little bit more involved, but still we can calculate that. So we know that there are a combination of 52 objects, 5 taken at a time, and that's the way to select 5 cards from a deck of 52. Now, if we want to draw only hearts, then we're selecting 5 hearts from the 13 possible hearts, which can be done in combination 13 objects chosen 5 at a time ways. So then that gives us the combination of 13 objects, 5 taken 5 at a time, divided by the combination of 52 objects taken 5 at a time. And you can see that it's a very small possibility. Now, 4 friends belong to a 10-member club. 2 members of the club will be chosen to attend a conference. What is the probability that 2 of the 4 friends will be selected? So the first thing is that we can choose 2 of the 10 members in a combination of 10 objects taken 2 at a time, so that's 45 ways. The next thing is that choosing 2 of the 4 friends can be done in a combination of 4 objects taken 2 at a time, which is 6 ways. So then the final would be 6 divided by 45, which is a combination of 4 taken 2 at a time, divided by the combination of 10 taken 2 at a time, or 2 over 15. So we have probability and genetics. So Y, capital Y, produces yellow seeds. That's the dominant gene. Lowercase g produces green seeds, and that's the recessive gene. So here we have parent 1, who's a YY, and then parent 2, who's a GG. So then the first generation then will be YG, 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 YG. Now, so crossing 2 first generation plants, so we have 2 first generation plants. So here we have what we call a Punnett square. So we have the first generation on the left hand side, and the first generation up on the top. So we do YG, YG. So then we have YY, YG, GY, and then GG. So then the first generation times the first generation will give us the 4 possibilities, which is YY, YG, GY, and then GG. Now, sickle cell anemia is a serious disease that's inherited. A person with 2 sickle cell genes will have the disease, but a person with only 1 sickle cell gene will be a carrier of the disease. Now, if 2 parents who are carriers of the sickle cell anemia have a child, then what is the probability of each of the following? So A is the child has sickle cell anemia, B the child is a carrier, or C the child is disease-free. So what we're going to do is we're going to go ahead and construct the Punnett square. So S denotes the sickle cell, N denotes a normal cell. So here we have the first parent, SN, the second parent is SN. And you see that we have SS has a disease, NS is a carrier, SN is a carrier, and NN is normal. So the probability that the child has sickle cell anemia is 1 out of 4, because that's the SS. And the probability the child is a carrier is 1/2, because there's 2 out of 4. And the probability the child is normal is 1 out of 4. Now, if the outcomes of a sample space are equally likely, then the odds against an event E are simply the number of outcomes that are against E compared with the number of outcomes in favor of E occurring. So we will write these odds as follows. So N of E prime to N of E, where E prime is the complement of the event E. So here we have, if a family has 3 children, what are the odds against all 3 children being of the same gender? So it's 6-2 or 3-1. So here we have 2 in favor, so boy, 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 girl, girl, girl. And then we have 6 against, which is, of course, that you have either 2 of 1 or 2 boys or 2 girls. So then the odds then in favor are 1-3. Now, a roulette wheel has 38 equal-sized compartments. 36 of the compartments are numbered 1 through 36, with half of them colored red and the other half black. The remaining 2 compartments are green and numbered 0 and 0, 0. A small ball is placed on the spinning wheel, and when the wheel stops, the ball rests in one of the compartments. So what are the odds against the ball landing on red? So there are 38 equally likely outcomes. 18 are in favor of the event, and when the ball lands on red, and 20 are against the event. So the odds against red are 20-18, or 10-9 if we reduce it. So the probability formula for computing odds. If E prime is the complement of the event, then the odds against E are probability of E prime divided by the probability of E. So if the probability of E is 0.3, then the odds against E are the following. So odds against E is equal to the probability of E prime, which is 0.7, divided by the probability of E, which is 0.3. So then it's going to be 0.7 divided by 0.3, or 70 over 3, or 7-3. So if the probability of Green Bay winning the Super Bowl is 0.35, what are the odds against Green Bay winning the Super Bowl? So G prime is the probability against, which is 0.65, and the probability in favor is 0.35. So therefore, using the diagram, we can compute that the odds against are 13-7. And that's the end of section 13.1. Thank you.